The title of this note is Inverse Functions, and the objective is to be able to calculate the inverse of a function if it exists 3 different ways: numerically, algebraically, and graphically. So an inverse function is a function that maps the output back into the input. So if you think about a mapping, here's all of your inputs, and then your f function maps them to all the outputs. An inverse goes the other direction. So an inverse takes the outputs and maps them back to the inputs. That green arrow is representing the inverse, and its notation is like this. That's read f inverse of x, and that -1 is like in the spot where an exponent would go. So let's take a look at a couple different ways to calculate an inverse. So the first is numerically. So we've got 2 examples here. In the first example, we have a set of ordered pairs. So this is our function. I'm just going to label that f of x. So there's our function. So what this means is that -1 maps to 0. 0 maps to -3. So the inverse would go backwards. It will map the 0 to -1. You take the output and it sends it back to the input. And so all you have to do is you list out every ordered pair, just switching the x and y. And then the last one will be 4, 5, which switches to 5, 4. So one of the things you want to pay attention to is if your inverse is a function. Remember your rule for a function, if you have a graph, it can pass the vertical line test, but every input has only one output. So there's a little problem here with this inverse. The input -3, right here it maps to 0, and right here it maps to 2. So you have one input with 2 different outputs. So this is an example where the inverse is not a function. FNC, that's short for function. So in example 2, also numerically, we have a list of numbers. This time we have a table. So now we're going to have x and f inverse of x. So all of the outputs, f of x, now become the inputs. And the inverse function will map it back to its former input. So -5 maps to 1, -3 maps to 2, and so on and so on. And you always want to check, do any of your new inputs have more than one output? This is indeed a function. So let's do it numerically. Next, we're going to look at graphically. So here we have a graph of the function, the square root of x. There is a table. The table might help you just to start. So just like we saw on the last page, the inverse would switch the x and y. So the inputs are now 0, 1, 2, 3, and the outputs are now 0, 1, 4, and 9. So if we were to plot those, I'm going to do it in red so you can see it clearly. Here's 0, 0, here's 1, 1, here's 2, 4, and then 3, 9 would be going to go off the graph up there. So if I were to sketch those with a smooth curve, I get something that looks like that. And what you need to notice is that these 2 graphs are reflections of each other over this diagonal line, which is y equals x. So inverse functions graphically reflect over y equals x. F of x and f inverse of x reflect over y equals x. So with that information, you can actually take any graph So knowing this pattern that it reflects over y equals x, you can now sketch the graph of the inverse of any function. So here's a graph, and I'm just going to sketch an arbitrary function. And what is its inverse? It can be helpful to sketch the line y equals x, and you're going to reflect. So if you imagine taking your graph, taking your piece of paper, and folding it along the blue line, what would the inverse look like? So I'm going to start here where it touches, and it's going to go kind of like that, and then over here, kind of like that. So that green is an example of the inverse. And you can imagine if I were to fold this piece of paper over the blue line, the green and the red would touch each other. Notice the green is not a function because it fails the vertical line test. The last piece of this is to do it algebraically. So algebraically, there's a couple steps. To find an inverse, what you're going to do is you're going to rewrite f of x as y. They mean the same thing. They mean the output of a function. And then in the second step, you're going to go ahead and switch your values x and y. And then solve for y again. And your last step, whatever answer you have, rewrite that as your inverse. So here's an example. Step 1, rewrite the f of x as the letter y. Step 2 is to switch the x and y. So this y becomes x, and that x becomes y. Everything else stays the same. Step 3 is to solve. Here's where you're implementing all of your algebra skills. I have a little trick for remembering how to solve. It's PEMDAS spelled backwards. So I'm trying to get y by itself. First I'm going to say, is there anything I can add or subtract? Notice p is at the end, so I can't touch those parentheses. But I can subtract 4 from both sides of this equation. And then I'm going to say, well, is there anything I can divide or multiply? Not that's outside of the parentheses. Is there an exponent? Absolutely. It's exponent 2. I'm going to remove it by taking the square root on both sides. Now that the y minus 2 is by itself, I can drop those parentheses. So when you get to the p, go back to the beginning. Is there anything to add or subtract to get y by itself? Notice that 2 does not go in the radical. So what we like to do is we like to write it in front of the radical just so there's no confusion between what's in the radical and what's not. So this would be 2 plus the square root of x minus 4 equals y. And then your last step is just to rewrite the y as f inverse. So that is the inverse function. If you want the f inverse on the left side, you can put it there. But it doesn't change the answer. So that's how you find an inverse algebraically. I'm going to put one more up, and I want you to find the inverse and bring it in class to discuss. So that 3 is under the radical, the negative 2 is not. Calculate the inverse. Pause the video here. I'll put the answer up in just a moment, and then bring it into class ready to discuss. This is the end of your notes.